This code snippet imports various Python libraries and tools for data analysis, visualization, and machine learning, including pandas, matplotlib, cbern, numpy, dim, dask, keras, tensorflow, and scikit-learn. It also includes utilities for preprocessing, training, optimization, and examining the current computing device's configuration. The code also sets up the environment for Jupyter notebooks to display plots and configures the aesthetics of cbern plots. Additionally, it may include custom utilities through a module named kzer. The Python code manipulates a variable called path by removing the last 10 characters. Assuming it is the substring notebooks, it then loads a CSV file called howSedDataProst CSV from the subdirectory data relative to the modified path. The data is imported into a pandas data frame named chidif and is expected to be tab delimited with a datetime column that should be parsed as dates. The data frame is then further processed to make the datetime column the index. A variable named magnitude is also set to 1, with a comment suggesting it should be adjusted based on analysis from a specific section of the code. This Python code converts 3 columns of a data frame, hour, day of week, and season to a categorical data type. Categorical data type is suitable for finite categories. This conversion can improve memory efficiency and benefit certain data analysis or machine learning tasks that treat categorical data differently from continuous data. This Python code snippet performs operations including manually splitting data into different sets, defining input matrix and target variable, and creating datasets for training, validation, and testing. It also plots the sets with corresponding labels and formatting, and saves the figure as a high-resolution PNG file. The x-axis is intended to represent datetime values, but this needs to be completed. The y-axis shows the gas power feature scaled by an undefined variable magnitude. Overall, the code snippet provides a visual representation of gas power consumption. This code creates a plot illustrating gas usage data using Python's matplotlib library. The figure size is defined as 20 inches by 10 inches, and the x-axis is indexed by datetime with the y-axis showing gas power values. The plot is drawn with red lines and dots with 50 opacity. The key label is datetime, and the A label represents gas power scaled by a magnitude and in cubic meters per hour. The tick label font sizes are set to 14, with the x-axis labels rotated for better readability. The title of the plot is mean gas usage of 52 houses, and the layout is adjusted to fit within the figure. This code is used to analyze and visualize gas consumption patterns for 52 houses over time. This Python code snippet creates training, validation, and test sets from a dataset called data for machine learning. The dataset is divided into features X and labels Y, with gas power as the label to be predicted. The training and validation sets make up 70 and 20 of the dataset, respectively, and the remaining 10 is allocated to the test set. The code calculates the indices to split the data based on these proportions and creates the respective sets of features and labels. The training set is used to train the model, the validation set is used for model evaluation during tuning, and the test set is used to assess the model's performance after training. The following Python snippet creates a time series plot that compares two datasets, train set and test set. The size of the plot is set to 20 by 10 inches, providing a larger figure for detailed analysis or presentation. The training and testing data are represented by red and blue dots and lines, respectively, with some transparency and labeled accordingly. The y-axis label shows the gas power measurement in cubic meters per hour, and the x-axis label suggests that the data represents datetime values, although this part of the code may still need to be completed. The font size and rotation of the tick labels are adjusted for readability, and a legend is added to differentiate the two datasets with increased marker size for better visibility. The Python code creates a neural network model using the keras library. It is a sequential model with layers stacked linearly. The input layer has 64 units. Truncated normal weights initialization, no bias term, batch normalization, and leaky ReLU activation. A dropout layer is included to prevent coverfitting. The code has 4 loops to add more layers, but they have no effect on the model. The code then adds alternating dense layers with different units. Batch normalization, leaky ReLU, and dropout layers. A final dense layer with 1 unit indicates a regression or binary classification task. The function returns the model. This snippet of code sets up the training configuration for a machine learning model in Python using keras. A function is used to create the model, and 3 hyperparameters are defined for the training process. A decay rate for the learning rate is also specified. Different optimizer configurations are set, and the model is compiled with specific loss functions and metrics. The batch size is printed at the end. This code sets up a Python-based training process for a neural network, using multiple callbacks to track and influence the training. This includes a high patience early stopping function, 3 model checkpoint functions to save the best models based on validation error, and a scheduler for learning rate scheduling. The model is then trained with various configurations, including a validation split and a list of callbacks. The goal is to train a deep neural network, save the best models, and potentially improve performance with adjusted learning rates. The Python code uses a magic command to measure execution time, imports a function from a specific module, and loads a pre-trained deep neural network model. Custom metrics are specified, and a potential issue is addressed by providing necessary custom objects. The model is then compiled with specific loss function and optimizer. Upon completion, the word finished is printed. This code is commonly used to prepare a pre-trained model for evaluation, fine-tuning, or prediction. This code implements a machine learning workflow by using a pre-trained model to predict outcomes and comparing them with actual results for a test dataset. The prediction results are stored in a variable, while another line of code ensures that the actual test outcomes are in the correct format. The full dataset is then split into training and test sets based on a specified proportion, and the relevant portions of the dataset are selected. Finally, the code checks for any inconsistencies between the test data subset and the array of actual outcomes. This Python snippet uses the matplotlib library to create a plot comparing real and predicted values, likely for a time series or dataset. It first sets up the figure and then plots the 2 sets of values in different colors, with labels and formatting for the axes. The code also evaluates the model on a testing set, generating error metrics which are then displayed in the plot's title. The plot serves as a visual representation of the data and model performance.